Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about polyprotic acids. So these are going to be acids that can give out a proton here, there, everybody gets a proton. So until now, we've been mostly looking at just acids that can donate single protons, like HCl. However, it turns out it's very common, especially in biology, to end up dealing with polyprotic systems. So one common example of these polyprotic acids is phosphoric acid. So this is going to be a phosphate group bound to 3 separate protons. So you may say, oh, phosphoric acid, that sounds like some weird industrial thing, but you probably have consumed phosphoric acid because it turns out it's what makes Coke so tangy and acidic. So Coca-Cola makes use of phosphoric acid. Now, it turns out the phosphoric acid is actually quite acidic because it has a pKa of about 2, which means we've got a very high K. So we're going to tend to predominantly dissociate. However, it turns out that when you do this, you're going to produce a fair bit of this H2PO4. So this dihydrogen phosphate. So this dihydrogen phosphate can then decompose and release a second proton to make monohydrogen phosphate. So as a result, this first pKa is called the first pKa, or the pKa of that first proton. The second pKa is going to be the pKa to lose the second proton. And you'll notice that this is going to happen with a much higher pKa or a much lower Ka. So it's not going to be nearly as acidic as the first. Now you may say, okay, why would I care about dihydrogen and monohydrogen phosphate? Well, it turns out that a mixture of these two species is very important for maintaining a good balance in your blood. So it's going to act as something we'll talk about later as a buffer, as it helps maintain pH, not to mention dihydrogen monohydrogen phosphate play an important role in helping drive ATP. Now, it turns out then this monohydrogen phosphate can lose a third proton to form a third pKa that's going to be even higher. So this means that this last proton really doesn't want to go with a fairly low K. Now, you might be saying, well, okay, why do I care about phosphate? That looks like something, belongs in rocks. Well, it turns out your teeth are close enough to rocks, as phosphate is part of a mineral called hydroxyapatite. And it turns out that hydroxyapatite is the major feature of tooth enamel. So if you ever wondered why the doctor tells you not to do things like drink soda or carbonated beverages, one of the reasons why is these carbonated beverages will end up adding acid. This acid can react with the phosphate in your teeth to make monohydrogen phosphate, which dissolves the phosphate in the apatite. So this is how you can get acid erosion, etching, or essentially decay of teeth. And it turns out that not only can things like sodas do it, the bacterial films that build up on your teeth, that tartar, ends up producing a little bit of acid as well, which again leads to tooth decay. So tooth decay is an acid-based function. So one of the things that's worth noting is we go through each of these Kas, you're going to notice that each Ka is smaller and smaller, which means that each proton is less likely to come off. This is often termed as it being more difficult to remove each successive proton. It's very easy to remove the first, harder to remove the second, and difficult to remove the third. And again, this is really what we're seeing with the Kas. So as a result, what happens is for most polyprotic acids, we're not going to actually start to lose that second proton until we've completely turned all of that phosphoric acid into dihydrogen phosphate. And then we're not going to end up turning the making phosphate until we've turned all the dihydrogen phosphate into the hydrogen phosphate. So each of these deprotonation events can be treated as a separate event. This has to happen, and then once all of this has been broken up, then we can start doing the second acid reaction and then the third. So one of the things we can do with this is we can use this to determine the amount of phosphoric acid, dihydrogen phosphate, monohydrogen phosphate, and phosphate in a solution to which I've only added phosphoric acid. See how much of each of these are formed. And really, this will give us a clue of, okay, if I have this reaction, how much do I need to worry about these subsequent reactions? So in order to do this, big surprise, we're going to make use of an ice table. And so if I start with phosphoric acid, I'm going to have to look at this first Ka, so this first acid reaction. And what we can do is use an ice table then to figure out how much dihydrogen phosphate and how many protons are released. So if I start with a 1 molar solution, we're going to assume that I'm going to have no dihydrogen phosphate and no hydrogen present. So then I'll decompose the phosphoric acid and produce my conjugate base and protons. And it works just like a normal ice table. We go ahead and plug it in. We're going to go a little loosey-goosey and assume that this X is fairly small so that we can then approximate my equilibrium constant as X squared over 1. Then we can go ahead and solve for X, which is going to be the same thing as both the conjugate base and the proton concentration. So when we do this, we'll end up with an X value of 0.087. So it is worth noting that this actually would significantly impact the value of the phosphoric acid. A good cutoff for when we could drop the X is 5%, and here we're sitting at about 9%. However, it turns out if you are going to run the math correctly, so do the quadratic equation, it would come out to be about 0.84. So for our purposes, this is going to be close enough. So we can then use this X value to determine the amount of free protons and dihydrogen phosphate present in solution. And then once we know the hydrogen concentration, we can then use this to help figure out the pH. Turns out that phosphoric acid, when put in solution on its own, is going to be quite acidic with a pH of 1. Yowzers, that's quite acidic. However, it turns out that that dihydrogen phosphate can break apart a little bit in water. So we're going to go ahead and take these two concentrations and plug them into another ice table. So now what we're going to look at is how much my dihydrogen phosphate breaks apart. But now instead of being a conjugate base, it's going to be the acid of this reaction. And it's going to end up producing monohydrogen phosphate and again, protons. And now we're going to use our second Ka, which again can be derived from our second pKa. We're going to go ahead and use this new ice table and plug in all our values. So the big difference from a lot of our previous ice tables is we're going to go ahead and start with a pre-existing amount of dihydrogen phosphate, but I've already generated a fair bit of acid. However, I shouldn't have any hydrogen phosphate, monohydrogen phosphate yet. So now we already have a little bit of product formation. So I'm going to consume a little bit of my dihydrogen phosphate to make a little bit of monohydrogen phosphate. And yes, I'll actually generate a couple more protons. So you'll note here, I'm using Y instead of X to show that this is a separate reaction. So the extent of this decomposition won't have anything to do with our first triprotic phosphoric acid decomposition. So then for the equilibrium line, we can go ahead and add up initial and change, and ta-da, we have a nice equation. So we could then go ahead and plug this into our equilibrium constant. And yeah, this isn't exactly too friendly. It'll make a quadratic, but not the worst quadratic equation. However, that's a fairly small K. So I can probably say that that Y will be small enough to ignore. So we're going to go ahead and truncate this as our Y times 0.087 divided by 0.087. Yep, it turns out those two terms will annihilate. So our Y, which as a reminder is our hydrogen phosphate concentration, will actually just be equal to our second Ka, because the amount of hydrogen, dihydrogen phosphate and free protons ends up canceling each other. So this will actually be true for most diprotic systems. The loss of the second proton, because the loss of the second proton is fairly minimal, that the concentration of your second conjugate base will be equal to the second Ka. In this case, very low concentration at about 6.2 times 10 to the negative 8th. Yep, that was definitely small enough to ignore. So since we have such a small amount of our dihydrogen phosphate and that Ka is so small, turns out that the dihydrogen phosphate and proton concentrations are going to remain relatively fixed. And now we can go ahead and try and figure out, well, exactly how much of my monohydrogen phosphate is going to go ahead and break apart. So using our monohydrogen phosphate concentration and our proton concentration and our third Ka, we can go ahead and set up another ice table. So for this ice table, it's going to be a little different than before because we got our hydrogen phosphate concentration from our previous ice table, but it turns out we still have the same proton concentration we did from our first ice table. So now when we're looking at the change in concentrations, we're going to consume a little bit more of my monohydrogen phosphate to make the make phosphate, and yes, a little bit more protons. Yep, I know that your initial concentration is pretty small, but now when we subtract Z, it turns out that's also going to be pretty small because that's a really small K. Similarly, our proton concentration won't change much. So what we're really going to focus in on is trying to determine the concentration of phosphate that is released by this reaction. So we can do this by, again, Z times each of those two terms, and assuming that the plus and minus Z in this case are fairly small. So when we do this, well, now we're a little bit more complicated of an equation than last time. However, we can get that phosphate concentration, again, Z in this case, by taking the concentration of our monohydrogen phosphate divided by our proton concentration times the third equilibrium constant. We go ahead and plug in those numbers, and yep, it turns out there isn't much phosphate at all. So turns out that when we're going to end up decomposing phosphoric acid, we're going to have a lot of phosphoric acid, a little bit of dihydrogen and monohydrogen phosphate, and very little actual phosphate present in solution. It's just simply too acidic for there to be any triprotic base present. So when you've got one of these polyprotic systems, it's very easy to get overwhelmed by the whole thing. So what we're going to do is break it down into little bits, put on our horse blinders, and use each problem individually. Do an ice table for the decomposition of phosphoric acid, then dihydrogen, then monohydrogen phosphate, and again, see how much protons we produce along the way and how much phosphate's released in the end. So for an initial concentration of 1 molar, we're going to, again, have a lot of phosphoric, a little bit of dihydrogen, very little monohydrogen, almost no phosphate, and a fair bit of protons. Since the second two reactions produced very little free protons, the pH is going to stay relatively fixed at 1.06. So that first decomposition reaction really tends to dominate the pH of a solution. However, it turns out that you can use this same basic approach of trying to find the pH of a polyprotic acid and switch it up to find the pH of a complex base, such as carbonate. So if I've got carbonic acid, it can go ahead and break up to form bicarbonate or monohydrogen carbonate and carbonate, so CO3 2-. So this is the key component of things like limestone. So that first pKa is going to be around 7 and the second around 12. So neither one of these reactions is going to be terribly acidic. However, if I go ahead and put carbonate in solution, I'm going to want to try and figure out what the KBs for this reaction are for. So the real trick when we're looking at KBs is realize that we're going to start with the carbonate, and then I need to work in reverse. So I can determine the KB by using the second acid constant, because this is the reaction that I'm going to be switching up. So your second Ka becomes your first Kb. And it turns out that this is actually going to be a pretty decent base. And then to get the second Kb, I'm going to have to flip that first acid dissociation reaction. And again, the biggest trick when working with polyprotic bases is figuring out which Kb corresponds to which Ka. And it can take a fair bit of practice to get used to. So if I'm going to go ahead and throw carbonate in solution, I can do a lot of these same processes. But now I'm going to use these two sequential protonation events. So we can do two sequential ice tables, the first for carbonate and then the second for bicarbonate. So using these values, we can determine, instead of the free proton concentration, the amount of hydroxide released, as well as the amount of carbonate that remains after decomposition, the amount of bicarbonate formed, and the amount of carbonic acid in the end. So it turns out you can use this same general approach for many real polyprotic systems, including carbonates, phosphates, things like oxalates, which we're going to use in lab. And carbonates is important as this is a lot of natural minerals, including limestone, and it's a major component of clay. Phosphate, while also present in a lot of minerals, plays a key role in the body with things such as ATP. And as the exact form of phosphate in solution changes, the exact energy efficiency of many sort of metabolic processes can change greatly. And again, oxalate is mostly going to be used in a lot of things like making inorganic compounds or kidney stones. And since I don't want to show you a picture of a kidney stone, here's the iron oxalate complex we're going to make in lab. So this is a real important thing to keep an eye out for. Not only can an acid or a base gain or lose one proton, but it can often do these actions sequentially. However, if you have the end product of either of these series go into solution, it's mostly going to be dominated by that first protonation or deprotonation event. However, it turns out that especially if I'm working with these sort of negatively charged anions, they aren't going to exist in solution alone. So next time, we're going to take a look at the acid-base properties of salts. Until then, take care.